In the last class we have designed for top chord as well as bottom chord. For top chord we have considered compression member, and bottom chord we have considered tension member as the nature of force given in the question itself. So now design of inner members. So inner members, if you look at the question, both compression as well as tension, both the forces are given. So what we are going to do here is, let us consider first initially inner compression member. For that, compression member force, member DJ is having force of 60 kilonewton. What is the first step we need to do? First we need to factor it. So factor load will be 60 into 1.5, that will be equal to 90 kilonewton. Same way, we need to make effective length from the actual length. So effective length will be 0.85 times L. So 0.85 into L is 3.46, which will be equal to 2.941 meter. 90 kilonewton and actual length is 2.941 meter. We know that for compression member, initially we need to assume FCD is equal, as it is a single angle, let us assume 50 Newton per mm square. So we know that PD is equal to area into FCD. The designed load we just calculated, that is 90 kilonewton. So 90 into 10 power 3, that is Newton, into effective area multiplied by FCD, which will give us effective area as 1800 mm square or 18 centimeters square. So what we need to do now? Now we need to select a angle from the steel table which suits to that area. From steel table, select ISA 100 by 100 by 10 millimeter, which is having effective area of 1903 millimeter square, which is obviously greater than 1800 mm square. So we can go with this. Along with the area, what is the R minimum value? That is least of XX and YY direction, 30.5 millimeter. 30.5 millimeter. We know KL by R, that is nothing but KL we have already calculated, that is 2.94 into 10 power 3 in terms of millimeter, and R is 30.5, which will be equal to 96.42. So if you go with the table, that is from IS 800, buckling class C, you will be having for 90 one value of FCD, and this is lambda value, this is FCD value. Same way for 121 Newton per mm square, and for 100, 107 Newton per mm square. So if you do interpolation, what is the value for 96.42? For 96.42, 2.042 Newton per mm. So for 90 it is 121 Newton per mm square, and for 100 it is 107 Newton per mm square. We wanted 96.42 lambda value. if you interpolate from these two values, we are going to get for 96.42 it is 112.012 Newton per mm square. And once we got this FCD value, we need to go back to this equation, that is PD is equal to, what is the area of 100 by 100 by 10 section? 1903 multiplied by FCD is 112.012, which will give us the design load as 213.158 kilonewton from the selected section and corresponding FCD, that is compression. This is what we are going to get, that is the area as well as the stress. So from these two we are going to get the design load will be 213.158 capacity for selected section. What is the actual load coming? That is 90 kilonewton, right? But the capacity is 213, which is obviously greater than 90 kilonewton. So it is safe. After knowing FUB and D, die of the bolt, D naught, die of the hole, and edge distance, we got 33. Let us round off to 40 millimeter. Then pitch distance 2.5 times the D, that will give us 50 millimeter. The next step is to calculate the bolt strength, that is in shear as well as bearing. To calculate in shear, we have a formula, that is 1 by gamma MB FUB by root 3 NNANB plus NS ASB. Let us consider the bolt will fail at the threaded portion itself. So shank portion, so FUB is 500 as we have considered 5.6 grade bolt. The strength of the shear strength of the bolt is 56.58 kilonewton. Same way in bearing, VDPB is equal to 1 divided by gamma MB, that is multiplied by 2.5 kb DTFU. kb is least of these values, that is edge distance divided by 3 times D naught, pitch distance divided by 3 times D naught minus 0.25, and ultimate strength of the bolt to the ultimate strength of the plate. If you do this, the least value will be coming here, that is 0.6. Add that to the kb value, 2.5 into, I have written here 1 by 1.25, 2.5 into 0.6 into 20 is the die of the bolt, and T is the thickness of the plate, and Fu is the ultimate strength of the plate. So in that case we got 98.4 kilo Newton. So out of these two, the least value is 56.58. So let us consider the bolt value as bolt value equals to 56.58 kilonewton. So number of bolts required equals, what is the load we have considered? Initial divided by force divided by bolt value. Force is 90 kilonewton and bolt value is 56.58 kilonewton, which will give us approximately 1.59 numbers. So let us round off to 2 number of bolts required to carry 90 kilonewton load. Okay, so this is how compression design part is over, and the next one is again for inner member we need to do tension design. Design of inner tension member, that is step is design of inner tension member. So for this also we have designed already, we have designed bottom chord as tension member, right? So same procedure you need to follow here. Only thing is the initially bottom chord we have considered different load, but here for the inner member 15 kilonewton load is there. For the, there are so many inner members, in that 15 kilonewton is the tension force given. So for that case clear span is also given, that is 2.31 meter. So let us factor this 15 kilonewton to get the design load. So 15 into 1.5 is 22.5 kilonewton. So now for this load we need to consider as the actually designed load. Okay. So now consider rupture strength of net section. Rupture strength of net section. So that rupture strength you need to equate this 22.5 kilonewton to get the area. Okay. So why do we need this area? Because we need to select certain angle, right? To choose angle we are going to equate this load with area. Okay. So now TDN is considering as 22.5 kilonewton and alpha will be 0.6 for 2 bolts, because we know that minimum 2 bolts should be provided for the connection, and Fu is the ultimate strength of the plate and factor of safety is 1.25. In this equation AN will be getting 114.32 mm square. For tension member we need to increase 30 to 50% of the area. So earlier case I have increased 30% and now I am going to increase 50%. You can choose anywhere between these two values. So 50% of the area means I am going to get 171.48 mm square. So to suit this area I am going to open steel table and check the angle which I am going to get is less than the 50 by 50 by 6 to suit this area. But I am not going to select that particular angle because I told you to select minimum 50 by 50 by 6 mm angle, that too single angle for intermediate or inner chord. Okay. So minimum 50 by 50 by 6 mm means what is the area of that? Area of 50 by 50 by 6 angle is 568 mm square. So what is the area we are getting? 171.48. that is very less, right? So no need to choose the angle which suits to this area. Go with the minimum angle what we have told, that is 50 by 50 by 6. Even though area is more, no problem, keep it 568 mm square. So next we need to find how many number of bolts required. For that we need to know what is the strength of the bolt. To know that, as this is a tension member, I am going with HSFG bolt. That is, this is the formula which is available in the page number 76. So here mu F is a plastic constant and number of shear planes, and this is also A and B is 0.78 into pi d square by 4 F naught, and F naught is 0.7 into 500. Okay. So A and B is 0.78 pi d square F naught is nothing but 0.7 FUB. Just substitute back to the equation. So next is we need to find out what is the strength of the bolt. For that I have assumed HSFG bolt and having 20 mm dia of grade 5.6. So with this equation available in the page number 76, everything you know, mu F and E is the shear plane. I am going to consider here as only single angle with the gusset plate, so only one plane will be there. So NE I am considering 1, and F naught is equal to A and B into small f naught. A and B is nothing but net area, that is 0.78 into pi d square by 4. Small f naught is nothing but 0.7 into FUB. All these are clearly mentioned in the code book. You can go through that one by one thoroughly. So VDSF, once I get every values, I am just putting that values into the equation. So 1 divided by factor of safety, that is 1.25, 0.55, 1 is the for NE and 1 for KH, and this is F naught value 0.78 pi d square plus small f naught value that is 0.7 into 500. If you solve this, we are going to get strength of the bolt as 37.73 kilonewton. So once we got strength of the bolt, next step is to calculate what is the number of bolts required. For that, number of bolts required is equal to what is the force coming to the bolt value. Force which we have considered in this case is 15 kilonewton after factoring 22.5 kilonewton. So 22.5 to the bolt value 37, we are going to get 0.59. Only one bolt is sufficient, but we are not going to give one bolt, but we have assumed that provide minimum 2 bolts for any connection. So in that way we have chose 2 number of bolts. Okay. So another 2 steps are remaining. One is due to rupture and another one is block shear failure. So check for rupture, under check for rupture, this is the formula you are going to get. TDN is equal to 0.9 ANC, that is connected legs net area, multiplied by ultimate strength of the plate to the factor of safety, plus beta into gross area of outstanding leg multiplied by yield strength of the plate to the factor of safety. So here only unknown thing you need to calculate is beta and gross area as well as net area. Rest of the things you can directly remember, right? So how to calculate this beta? To calculate beta, again there is a huge one more formula, that is 1.4 minus 0.076 into W by T multiplied by Fy by Fu multiplied by Bs by Lc, which should be less than or equal to Fu gamma m0 to Fy gamma m1, which should be greater than or equal to 0.7, which is available in the code book itself. So if you want to calculate all these terminologies, you should be in a position to understand or draw this figure. So if you understand this figure, see 2 bolts we got in the previous step. So those 2 bolts we have placed in the angles. Angle is having 50 by 50 by 6 mm, which we have considered. In that, see what is LC? LC is length of the connection, that is between 2 outermost bolts. If instead of 2, if 5 bolts are there, because we have did this in the bottom chord member, 5 bolts was there in that place. So what we considered from initial bolt to the 5th bolt, center to center distance we have considered. Same way here only 2 bolts are there. So between these 2 bolts, whatever the pitch distance available, that will become length of the connection. So what is length of the shear plane? Length of the plane will become these 2 bolts plus edge distance, that is 100. So this is in the direction of shear. The perpendicular or transverse direction LT can become 22. That will be from center of the bolt to the edge of the plate in the transverse direction or perpendicular to the shear direction. So what is W? W is the overall depth of the section or angle, that is 50 millimeter, and W1 is where the bolt is inserted from the face of the angle. So W1 will become 28. How it is 28? 22 plus thickness 6 mm plate. So 22 plus 6 is 28. So what is BS? BS is equal to W plus W1 minus T. W50 we just got to know, plus 28 minus 6 millimeter will give us 72, and these values will be put in this equation, that is beta equation. W will be 50, which we have already calculated, and T is thickness of the angle 6 mm, Fy is yield strength 250, Fu is ultimate strength 410, BS is 72 millimeter, and LC is length of the connection, that is 60 millimeter, and which should be less than or equal to ultimate strength 410 to the factor of safety 1.1 divided by yield strength 250 to the factor of safety 1.25. So if you solve this beta, we are going to get 0.936, which is obviously in the satisfied condition, that is which is less than or equal to less than 1.44 and greater than 0.7. So we can consider 0.936 as beta value, and we got this beta. Next step is to calculate AG naught and ANC. How to calculate AG naught? AG naught is nothing but outstanding angles gross area. Gross area is nothing but the breadth 50 minus thickness by 2, that is C, in this line, center of this angles line, you need to calculate the area. So what is this depth? 50 multiplied by the thickness is 6 millimeter. I am deducting this thickness just because I am considering in between this, exactly at the center. So breadth or 50 minus thickness by 2 multiplied by the thickness will give us gross area. In that, if we want net area, we need to deduct that whole area where we are going to insert the bolt. So that bolt area I am deducting in the net area of overall from the gross area. So once we got these two values, that is net and gross area as well as beta value, let us put those values into the original equation, that is TDN. We are going to get 104.52 kilonewton, which is greater than 22.5 kilonewton, which we have considered for the design of inner chord member, or the force given. Force given is 15 kilonewton. Once we factored it, we are going to get 22.5 kilonewton, but actually in this condition what we have considered is 50 by 50 by 6 millimeter angle. For that angle the carrying capacity is 104 kilonewton, so it is greater than 22.5, hence whatever we considered is okay to resist this rupture condition. And the next condition is block shear failure. So the next step is check for block shear. Under check for block shear, we have placed the bolt as we considered in the previous step, that is check for rupture. In this case, if you look at page number 33, you will be getting check for block shear formula, that is TDB1 is equal to AVG Fy by root 3 gamma m naught plus 0.9 ATN Fu by gamma m1. Here, or TDB1 and TDB2, these are the two formula. Again, in these two, any one of the value which is least value you should consider for the design. And here, if you look at the equation clearly, only unknown thing you will be able to find here is only this gross area in the shear lane and net area in the transverse direction, as well as gross area in the transverse direction and net area in the shear direction. If you find these four areas, it is very easy to substitute and calculate the remaining values, because Fy is the yield strength 250, you can remember easily, and gamma m naught is the factor of safety 1.1, Fu is the ultimate strength of the plate, that is 410, and factor of safety 1.25. So these values you will be easily remembering. Only you need to calculate here is this gross area as well as net area. So how to calculate that? To calculate gross area in the shear direction, as we did in the rupture case, shear direction means parallel to the bolt or in the direction of the bolts, that is length of the shear means 60 plus 40 from this point to the edge of the plate, 60 plus 40 is 100 multiplied by thickness 6 millimeter will give us 600. That is gross area. If we want to calculate net area, AVG, next AVN. How to calculate the net area? To calculate net area, in the gross area you need to deduct just those two bolts area, right? So number of bolts minus 0.5 into T is the thickness of the plate and D naught is the dia of the hole. If you do so, you will get net area in the shear plane. Same way in the transverse direction, net area as well as gross area. How to calculate gross area in the transverse direction? That is from this point to this line. What is the area? We know that 40 is there from here to here. Sorry, not 40, it is 22. From 22, what you need to deduct? You need to deduct only this portion to get the net area. If you want gross area, directly from this point to edge, that is 22 multiplied by the thickness 6 millimeter will give you gross area. If you want net area, in that gross area you are going to deduct half of the dia of the hole multiplied by the thickness. That is how much? 66 millimeter square. So once you found all those four areas, just substitute back to the equation. If you substitute back TDB1, you will be getting 98.212 kilonewton. Same way TDB2, you will be getting 117.71 kilonewton. In these two, which is the least value, obviously it is 98.212. So TDB value will be considering 98.212. What is the load we have considered? We considered is 22.5 kilonewton, which is given in the question itself. So this value is obviously greater than this. So the condition is satisfied. The next step is design of anchor bolts and bearing plates. Okay, in continuation with the previous step, the next step is design of supports. So in design of support, there will be two things we need to do. One is base plate or bearing plate dimension, that is area as well as the depth, and also the anchor bolts we need to design. That means to say what is the dia of the bolt and what depth it should go inside the concrete column or RCC column. So here what you are able to see is a bottom chord of the truss. Okay, and this one is top chord of the truss, and these two are resting on the RCC column. So at this corner we need to fix or we need to support these two in such a way that they should be stable. So for that, first thing we need to fix the bearing plate. What is the area of the bearing plate as well as depth of the bearing plate? That is what we are going to do now. Okay. So under bearing plate, once we understand this terminology, that is bearing plate and anchor bolt and the purpose, let us move on to how to design this area as well as the depth of the bearing plate. For that, we know that bearing capacity of the concrete is 0.445 FCK, 0.45 FCK. So FCK considered as 20 Newton per mm square. For that, we got bearing capacity as 9 Newton per mm square. So let us provide square base plate over the RCC column. For that square base plate area, first we should understand area of base plate is nothing but load divided by bearing capacity. So what is the load we should consider? Anyhow, bearing capacity we got that 9 Newton per mm square. But what is the load that we should consider? That load is nothing but what is the reaction developing in the truss, which was given in the earlier, that is in the question itself. If it is not given, the load will be given. According to that, you need to calculate the reaction. But in this case, it is given, that is 120 kilonewton. 120 kilonewton. For that, we are going to factor that 120 kilonewton, that is 1.5 into 120 will give us 180 kilonewton. So what is our formula to calculate area of base plate? It's a basic area is equal to load divided by bearing capacity. Load is 180 into 10 power 3 Newton divided by bearing capacity is 9 Newton per mm square. So area is equal to 20 into 10 cube mm square. We have assumed that, let us provide square base plate. So side is equal to square root of 20 into 10 cube, which will give you 141.42 mm square. So let us round off the value to 200 by 200 by 200 by 200 mm as the square base plate in the plan. So this is 200 and this is 200. So area of the base plate is over. What is the next thing? Next thing is to decide what is the depth of the base plate. For that, we need to understand, first we should understand this diagram part, how the angle is fixed. If you observe the diagram properly, see there are two angles which we have considered by assuming two ISA 70 by 70 by 8 millimeter for the connection of bearing plate. So here just assume from here to here it is how much? 70 millimeter. Same way from here to here it is 70 millimeter, and thickness of the plate is 8 millimeter. What is the total width of the bearing plate? That we have already calculated, that is 200 millimeter. From the center to this corner how much it is? It will be 100, right? So exactly at the middle. Same way, what is the thickness of the base plate? We don't know, we need to calculate it, right? But what is the thickness of the angle? 8 millimeter. What is the overall thickness? Overall thickness will be 8 plus t, that is 8 plus t, isn't it? So what we want to know here is how to calculate the thickness. Usually thickness will be depends on the load coming over it, correct? So the load whatever developing here is from the bottom, that is reaction. So reaction is nothing but, or how to calculate that? Q naught is equal to load divided by area. What is the stress developing from the bottom? So now that load we should consider as 180 into 10 power 3, 180 kilonewton. What is that 180? Reaction was how? 120 kilonewton. So once we factored, we got 180 kilonewton divided by the area of the base plate is 200 into 200, which will give us 4.5 Newton per mm square. Stress is developing at the bottom. So if we want to fix that, let us consider moment at one particular point and consider this portion as cantilever portion. Why am I considering here means from this, okay, this is the gusset plate. After gusset plate, one angle will be there, angle thickness. After that, root radius, deducting root radius at that corner where you will get the flat surface. At that point only you should consider the axis to calculate the cantilever moment. Okay. So to calculate that, come here, consider 1 millimeter strip. Let us not consider the whole thing. Consider first 1 millimeter strip and calculate for 1 millimeter strip what is the depth is required. So Q naught will become 4.5 Newton per mm square per 1 millimeter into 1 millimeter. So which will give us what? It will give us UDL load, uniformly distributed load, that is 4.5 Newton per millimeter, that is acting at the bottom of the base plate or bearing plate. So Q naught will become 4.5 Newton per mm. So now how to calculate bending moment at this corner? This is nothing but what we have considered the axis here, XX axis, okay, and which is having at a distance of, what is this, 200 by 2? Total is 200, half of that is 200 by 2 minus 5 means half of the gusset plate, that is 5, and minus 7 is the thickness of the angle, and minus 8 is the root radius. Okay, this root radius is 8, which will give us 80 millimeter from the end of the bearing plate. So how to calculate bending moment? 4.5 multiplied by the distance here is 80 millimeter. So as it is a UDL, WL square by 2, that is 4.5 into 80 into 80 by 2, which will give us the moment 14400 Newton millimeter. Okay, once we got the moment, we know that from the IS 800 page number 53, for design moment there is a formula MD is equal to 1.2 ZEFY by gamma m naught. In this equation, ZE will be the criteria for thickness, criteria to calculate the thickness of the bearing plate. Okay, so now in this case ZE is the unknown thing. ZE is nothing but section modulus, that is I by Y. I means BD cube by 12 and Y is D by 2. After solving this, you will get BD square by 6. So what is the breadth? Breadth we should consider, we have considered 1 millimeter strip. So I am using breadth place 1. And what is the depth? Depth I am using from here to here, that is 8 plus T. Overall 8 plus T is the depth, whole square, BD square by 6. So if you solve this, you are going to get, for design moment, what is the value we should use? 14400. 1.2. For ZE, we are going to use this equation, that is 1 plus 8 plus T whole square divided by 6 multiplied by yield strength divided by factor of safety 1.1. So in this equation, only unknown thing is T, thickness. So if you solve this, you will get T as 9.79 millimeter. So let us round off that to 10 millimeter thickness of the plate. That means to say this plate thickness is 10 millimeter. This thickness is 10 millimeter. So we got all the values, that is provide 10 mm thick and 200 mm square plate. That can also be written as 200 by 200 by 10 mm. Okay, with this bearing plate design is over, and the next step, that is first one was bearing plate or base plate design, and second thing is anchor bolt. What is the depth it should go inside, and dia can be assumed. So in the next step, that is anchor bolt design. For anchor bolt design, we know that anchor bolt will be provided from the base plate to the concrete, that is RCC column, to hold the base plate as well as the angles in a position. So to design anchor bolt, first thing we need to understand is what is the uplift force. Uplift force is given in the question, that is 15 kilonewton. So out of 15 kilonewton, we need to provide 4 bolts. Let us consider. For 4 bolts, what is the each bolt carrying capacity of from this load? 15 divided by 4, which will give us 3.75 kilonewton. So one bolt will be carrying, consider 3.75 kilonewton. Let us factor that 3.75. So if you factor that 3.75, we are going to get 5.625 kilonewton. Now consider this is the ultimate load which we should design the anchor bolt depth. So now what is the external force, or what is the resistance developing? Resistance developing is nothing but external force applying on the body, correct? So uplift force is equal to circumference of that particular thing multiplied by height multiplied by the bond stress, which is available in the page number 42 and 43 of IS 456. So if you go with this page numbers, you will get tau BD value for FCK 20 Newton per mm square as 1.2 Newton per mm square. So we need to increase that 1.2 Newton per mm square by about 60% as the code says. So 60% of 1.2 plus 1.2 will give us 1.92. So final tau BD value is what? 1.92 Newton per mm square. So next let us adopt 16 mm dia bolt. Let us adopt the 16 mm dia bolt, and this is the formula, that is uplift force is equal to circumference multiplied by the height into bond stress. Bond stress is nothing but tau BD. So uplift force we already calculated, that is 5.625 or 5.63 if I rounded off. So 5.63 into 10 power 3 newtons, which is equal to circumference is nothing but pi d, circumference of the bolt, multiplied by height, which we want to calculate, depth. Suppose if this is the base plate, means from the base plate at what depth it should go inside the RCC column. If you consider this as the RCC column. So multiplied by tau BD is the bond stress, which we have already calculated. Substitute everything. Only unknown in this equation is H, that is depth of the bolt insertion, which will give us 58.34 millimeter. We can round it off to 60 millimeter depth in this way. From the bearing plate inside the RCC column, it should go height of 60 millimeter. Okay. So with this, the design of truss completes. So what we did from the beginning? From the beginning, initially we have identified what are the top chord members and bottom chord members as well as inner chord members. So in that, for top chord, what is the nature of the force given, we should notice. Okay, only compression force is given, or along with the compression tension force is also given or not. We should notice that. If both the forces are given, in the top chord, then we should design that top chord for both tension as well as compression member. If only one force is given, we should understand which is the most or maximum force, and for that force we should design depending on the nature of the force. Same way for the bottom chord as well as inner member. So once top chord, bottom chord, inner chord is over, the next step is to design the bearing plate to fix that into the RCC column, okay, to make some platform. So once the bearing plate design is over, the last step is to fix the anchor bolt inside the bearing plate as well as the RCC column. So this is how the anchor bolt will be calculated, or the depth will be finding out, and with this design of truss will be completed. Thank you.